all the res- okay to welcome all the respected dignitaries, faculty members, guest speaker, and enthusiastic participant to this national level webinar organized by students of ISHRE Pune chapter, Department of Mechanical Engineering, Jai Hind College of Engineering, Kuran. So I welcome Dr. Binu KG sir. So we have speaker with us. Then I welcome Professor Paresh Pawar sir, Head of Department Mechanical Engineering, along with Mr. Subhash Khanade sir, President of ISHRE Pune chapter, all the respected teachers and enthusiastic participants. So today we are here to explore an exciting and important topic in engineering, similitude and model analysis in fluid mechanics. So we have Dr. Binu KG sir is a professor in the Department of Mechanical Engineering at St. Joseph Engineering College, Mangaluru. He is also the head strategy and planning of the institute. He holds a mechanical engineering degree from PES College of Engineering, Mysore University, and post graduation MTech in Maintenance Engineering and SJCE, Mysore, VTU. He has completed his PhD in tribology from MIT Manipal. His research interests are in hydrodynamic lubrication, nanofluids, ocular tribology, and engineering education research. He has 26 international publications to his credit. Two of his papers were awarded the best paper in international conference. He is a certified international engineering educator with certification from IGIP Austria and IUCEE. He is a certified master facilitator in human resource development from the College for Leadership and Human Resource Development, Mangalore. So we are truly honored to have such a accomplished expert with us today. So I welcome you, sir.
Thank you, Ashwini.
Yes. So I request Professor Paresh Pawar, sir, to share few words with us. Hello, sir. I request Pawar, sir. Hello, sir.
Yes, thank you, Ashwini. Sorry for the inconvenience. Am I audible?
Yes, sir.
Okay. So, good evening to all. On behalf of Jai Hind College of Engineering and our Mechanical Engineering Department, it gives me a great pleasure to warmly welcome for our today's national level webinar on similitude and model analysis in fluid mechanics. I extend a very special and heartfelt welcome to our distinguished speaker, Dr. Binu KG sir. We are truly honored to have you with us, sir. Your extensive experience in mechanical engineering, particularly in area like tribology, hydrodynamic lubrication, and nanofluids, is deeply inspiring. We are confident that your insights will greatly enrich the knowledge of all the participants. I would also like to express my sincere gratitude to our respected principal, Dr. A.B. Wade sir, for sir constant support and encouragement. Also, I extend my regards to our Honorable CEO, Dr. D.S. Galle sir, and our Director, Dr. H.D. Gunjalman, for their visionary leadership and continuous motivation in organizing such academic events. Also, I would like to specially appreciate for the taken these efforts to our program coordinator, Professor Gordon B. for their successful organizing such a webinar. I also warmly welcome all faculty members, students, and participants who have joined us from various institutions across the country. Your presence reflects your enthusiasm for learning and advancing in the field of fluid mechanics. Our today topic is highly relevant, forming a strong foundation for both academic understanding as well as practical engineering applications. I am certain that this session will provide valuable perspective and deepen our conceptual clarity. Once again, I welcome our esteemed speaker and all attendees. I wish everyone a highly informative and engaging session. Thank you.
Thank you, sir.
Thank you, sir, for your guidance. So I now request President of ISRE Pune chapter, Mr. Subhash Khanade, sir, to address the students.
Uh,
Hello, sir.
Hello, Ashwini, please skip this session. Sir is unavailable right now. Hand
Okay,
over to
then.
hand over to the sir.
So we are truly honored to have such a accomplished expert with us today to guide us through his subject. So without further delay, let us begin this enriching session with great enthusiasm. So I request Dr. Binu KG sir. So now
Yeah.
over to you, sir. Thank you, sir.
Thank you, Ashwini, for that wonderful introduction and for setting up this webinar. And good evening to everyone present here. Uh, Let me also welcome all of you to this webinar on similitude and model analysis in fluid mechanics. Just a quick check. Am I audible in now? Is my voice clear?
Yes, sir. It's clear.
Okay. And the slide is also visible, right?
Yes, right.
Okay. Then let's begin. Okay. So before I begin at the outset, I would like to thank Professor Nishigand and the ISRE Pune chapter and the students chapter as well for giving me this opportunity to interact with all of you. It's an honor, and I am grateful for that. Now, just to save bandwidth, I will be switching off my video. For the duration of the lecture, and during the Q&A mode, I will switch on the video. I hope that is okay with all of you. All right, so let's now begin. Today we are going to discuss a very interesting part of fluid mechanics. I know most of you are students of fourth semester. You are all in your second year of mechanical engineering, and this is a course that you are studying in this semester. Okay, uh, it is a wonderful subject. It is a course where theory and experiments, design, safety, and most importantly, a lot of common sense will all join hands. Okay. Now the title of my webinar is similitude and model analysis. Now in simple words, what we will be asking is how can a small model help us predict the behavior of a large real system? If you look at the slides, at your top right, you will see a dam, isn't it? Which is a massive structure, right? Now, below that, you can see a small model of that dam, which is in a laboratory scale, all right? Now, how can I predict the performance of a real scale dam by studying a small model in the lab, right? So, how does that work? Okay. Now, this is what we will be learning in similitude and model analysis, right? I will keep it short. My intention is to finish it within 45 minutes to 1 hour. Then we will have a Q&A, and then we will proceed. All right. So let's go forward. Second. All right. So as it was introduced, my name is Binu KG. I am a faculty. I'm a professor in the Department of Mechanical Engineering at St. Joseph Engineering College. And fluid mechanics has always fascinated me. Okay. because it is like everywhere, right? Wherever you see, fluid mechanics is present. Okay, it is in the machines that we develop. It is in nature. It is inside our body as well, right? And sometimes you will experience fluid mechanics in your classrooms as well, right? When you switch on the fan, and if the air doesn't reach the last benches, right, then that is a fluid mechanics problem. Okay, so you have all experienced fluid mechanics even before you began this subject. All right. So my plan of presentation is, uh, I would begin with a summary of fluid mechanics, just to give you an idea of where you stand. As far as I understand, you have done with module 4, okay, and you are now entering into the module 5, and I just want to present you a quick summary of what you have studied so far. Then we will discuss what is meant by prototype and what is meant by model, and why do we need to study and why do we need to know about similitude. All right. Naturally, to understand similitude, you also need to know dimensionless numbers, right? So, what are these dimensionless numbers, and how is it applied? We will have a quick look at that. Okay. Then we will also, go through few numerical problems, few applications of similitude and model laws. Okay, and then we'll have a quick Q&A, and we will end the webinar. Okay. I see a mark there on my slide. Can I just stop it for a minute and then restart it? Give me a minute. All right. Can someone confirm if the slides is visible?
Yes, sir.
All right. Okay. So as I was saying, fluid mechanics is like everywhere. Okay. So actually, fluid mechanics is life. Okay, every breath that you actually take, the flow of air through your body, that airflow, it is governed by fluid mechanics, right? Every heartbeat, which enables blood moving through your body, it's also governed by fluid mechanics. Okay, so everything that you see all around you in your day-to-day life, you will experience activities which are governed by fluid mechanics. Okay, therefore fluid mechanics is very serious, all right, and at the same time it is also beautiful. Okay. Now, can I just ask you one quick, simple question? Can you give one example from your daily life where fluid mechanics is like involved? I want this session to be like interactive, so please quickly get on to that chat box, and you can, give me your answers, right? So can you give me one simple example from your daily life where fluid mechanics is like involved? Right? So it will be great if you can, reply in the chat box. All right. So while we wait for you to do that, there is plenty of such applications. Now, say for example, uh, when you're breathing, right? When you draw that air into your body, that is also, an example of fluid mechanics. In the same way, blood flow, as I said, then flow of rivers, both natural and open water channels also exhibit behavior which is governed by fluid mechanics. Weather, formation of clouds, and the like, movement of clouds is governed by weather. Then most of the machines, especially the turbo machines, pumps and turbines that we run and like operate, they all function based on fluid mechanics. Okay. Now moving on. Uh, Fluid mechanics, I'm sure you would have learned so far that it is governed, it can be classified into three fields of study. And these, I would term it as the three important pillars of fluid mechanics. First one is statics, then you have kinematics, and then dynamics. Okay, you would have studied all these three. Okay, statics largely deals with fluids at rest. All right, kinematic deals with fluid motion without taking the cause of motion. We don't discuss the forces, but rather we will describe the motion, right? And in dynamics, we take into account the forces, right? We will also take into account pressure, and we will study the motion as well, right? The forces plays a major role. Force and pressure plays a major roles in fluid dynamics, right? And then clear understanding of all these three fields of study is essential for you to become an expert in fluid mechanics. All right. Now, in Unit 1, you would have studied fluid statics, right? One of the most important law that you have studied in fluid statics is the Pascal's law, right? Which gives you the equation for pressure at a point within a static fluid body, okay? Which is given by rho g h, okay? Now, this Pascal's law has got wonderful applications in terms of force magnification and force transmission. Say, for example, when you will press a brake in your vehicle, right? You are actually designing it using Pascal's law, which states that force is transmitted equally in all directions, right? So when you step on that brake pedal, right, the fluid from the pedal cylinder gets transmitted to the wheel cylinders, right? And that actions, apply force on the wheels, which will result in the braking action. All right. So this is one of the applications of uh, Pascal's law, which is an essential part of fluid statics. In fluid statics, the key variable is pressure, right? Now, if you look at fluid kinematics, we largely deal with streamlines. Okay. Now, what do you mean by streamlines? Okay, a streamline is a path that is followed by fluid uh, particles at any given instant, right? Therefore, say we are going to describe fluid motion without taking into account the forces that will act, right? So it just tells us how fluid flows. Okay, the key variables here will be, say, velocity and acceleration. Okay, acceleration and velocity, these are the two primary variables we will be studying here. All right, so it just tells us how fluid moves. Okay, say for example, if you will look at a Formula One vehicle, all right, we would be interested to know how fluid flows over the structure, right? So that we can identify those regions which will induce drag, and can we modify the structure so that the drag is minimized. So to understand that airflow, right? To understand the flow of fluid around and along the structure, we make use of fluid uh, kinematics, right? Then comes the most important area, which is fluid dynamics. And I'm sure all of you have studied Bernoulli's equation this semester, a wonderful equation which has allowed humans to build so many wonderful fluid applications. All right. And the Bernoulli's equation essentially gives you the relationship between variables such as pressure energy, right? And then kinetic energy and potential energy. It basically states that the pressure, kinetic, and potential energy, the sum has to remain same, right? Therefore, this will lead you to that important insight that if velocity will change, the pressure will also change. right? So this is what you have studied in fluid dynamics. Okay. Now going forward, we now enter into using this Bernoulli's equation, you can understand why airplanes fly, right? You can actually see that because of the difference in velocity, right, we will create pressure differences, and it is the pressure drop that provides the lift, right? So that's one of the reasons why aeroplanes fly. We also look at why fluids will accelerate. We also look at why there should be pressure change. All right, that is like also an important application, right? So to summarize where you stand, you have studied fluid statics, you have studied kinematics, and you have studied fluid dynamics also. Therefore, you have looked at fluid which is at rest, you have looked at the motion of fluid particles, and you have also studied the fluid forces. All right, so this is where you stand. Okay, now what I want to know from you is by understanding this fluid behavior, is it possible for us to predict real systems? Okay, because when you are engaged in engineering, you will have to apply this knowledge to build and to operate something, isn't it? So the key thing to ask is, how do I apply this knowledge to something that I cannot test directly? Say, for example, a dam, right? I cannot build it and then test whether it will work or not, right? Now that will be dangerous, isn't it? So what do we do then? Therefore, the problem that we are dealing with is I cannot test a real dam. I cannot test a full flight, a like full aircraft. I cannot build and then test whether it will work or not. Dangerous. Right? I cannot test a full river. It's massive, right? So what do we do then? So what does engineers do? They build models, right? So this forms the main topic of the day, that to understand the performance of a prototype, right, we will build models and then we will study them. And through that model, we will predict the performance of the prototype. All right. So what you see in this image is a model of this full scale. Let me just open the marker here, just a second. Oh, I'm sorry. My bad. My mistake. Let me just a second. I'm sorry. Just hold on for a second. Let me share my screen again. Yeah. I hope the screen is visible now.
Yes, sir.
All right. Okay. Okay. So as I was saying, to test these structures, we actually build models. Therefore, you can see that the model is a scaled down version of an actual uh, aircraft, and we test it inside a wind uh, tunnel, which I'm sure all of you would have seen, right? Where we will study how fluid forces will act on the model, right? Therefore, we can make appropriate predictions on the actual real aircraft. Okay. Now, why is it needed? Because we all know that aircrafts are very expensive. Okay. Usually, a commercial aircraft is somewhere between 700 to 1,500 crores. Okay. Military fighter jets is between 1,000 to 2,000 crores. Okay, say for example, our Rafale is estimated to be somewhere about 1,600 plus uh, crores of rupees. Okay, therefore we cannot prepare the prototype and then check if it will work or not. Again, that is not how we do like engineering. What we do is we will build a model, right? And this model cannot be randomly made, if I will ask you, would you sit in a plane that was never tested before, right? All of you definitely say no, absolutely no, right? No matter what free seats they will provide, you will still never enter that plane, right? So that is why similitude and model analysis is very important. Okay, now let us look at what is meant by these terms. What is a prototype and what is a model, right? On the left side, we have got three prototypes. Okay, that is a full scale passenger aircraft. And on the right side, you see a wind tunnel scaled down model of that aircraft. The same way you have a full scale ship on the left. To test its performance, we have a scaled down model of the ship, right? Similarly, you have a full scale dam along with the spillways, and you have a similar model which can be operated inside a lab, right? Therefore, this is what you see as the difference between prototypes and models. Therefore, what we really mean is prototype is the real system, right? It is the actual dam, aircraft, or ship, whereas model is either a scaled up or a scaled down version which is used for performance analysis. All right. So the difference is models are lab operated, scaled down version, whereas prototype is the actual real structure. Okay. I've got a small little video here to play, which will show you how they test models, to actually predict the behavior of a real the prototype. I'll just play this video. Please have a look. Let's check if it works. Able to play it. Just a second. Yeah. All right. So that video shows how a wind tunnel test is done on a model spacecraft or an aircraft. Okay. I've got a video of how they test a ship, which we will see if time permits towards the end of the presentation. So with this, you understand that what is the difference between a model and a prototype. Now, what I want to ask you is, if I test a small model, will it behave exactly like the real aircraft? What do you say? Is it possible for you to interact with me? Can you enter in the chat box? Can you say, will it behave exactly? Shivtej is saying no, sir, right? Uh, and Hussein is saying not possible at all right? Absolutely. Okay. Now, can I ask you why? Why will it not exactly behave like the real structure? The main problem is, by default, model is not equal to the actual physical structure. It will never be. Okay, we will see why, right? This is the reason why we need today's topic, uh, similitude. Okay? A model is only useful when it behaves exactly like the real structure. Okay, and this is possible only we when we design models by taking into account principles of similitude and model analysis. Okay, so what engineers typically do is, when the cost of failure is very high, okay, we will have to build and we will have to rely on models. Okay, so I hope it is clear why we need model analysis. Okay, now let us just quickly think why by default model is not equal to the reality. This is because, say that I prepare a model which is 1/10 of the actual structure. So I have scaled it down to 1/10. Okay. Will the design always be proper? Answer is no. Okay. Why will it not work? Because only scaling the geometry will not make the design proper. Okay. Because for the model to work or to be an actual representation of the real structure, the forces should also be similar. The forces should also be proportional, right? And we all know that forces don't scale linearly, right? And even fluid behavior, fluid behavior will not scale directly when you scale the geometry. Just because you are making the model small, that doesn't mean that you can apply smaller forces or smaller velocity or smaller viscosity on the structure. That won't work. Okay, most of the fluid properties such as gravity, viscosity, and velocity, its effects will differ when it is on a full scale and when it is on a model scale. Okay, therefore, direct scaling of geometry alone will not solve the problem. Okay, I'll just give you a small example. This will help you understand why direct scaling won't work. Okay, now suppose if we have a 10-storied building, okay, and this building is 30 meters in height. All right. Now, if a human being fall from the top, absolutely it will be fatal, right? The human will die. Now, suppose if I scale it down, right? This 30 meters, I will proportionally make it to 3 centimeters, right? I will scale it down significantly, okay? And I will scale the human also now, okay? I will scale the human to the size of an ant now, right? Now, if that small ant-sized human, if it will fall from this 3 centimeter tall, building, uh, will something happen to him? No, he'll be safe now. All right. So I have directly scaled it. Okay. But the end effect is different. Why? Because the physics changes. Right. Geometric scaling, will also change the physics. Right. Say, for example, when the small ant-sized human will fall, the air resistance becomes more important, right? The mass is now becomes very mass of that smaller human becomes very less, right? Therefore, the end effect is also not the same. Okay, this is where principles of similitude becomes necessary. Okay, all right. Now, how do we define this? What do we mean by similitude? All right, similitude basically it refers to the similarity between a model and a real system. That is how similar is the model to the prototype. Okay, a like more clear definition is that similitude exists. Similitude exists when a model and prototype will exhibit similar behavior when all the physical parameters that are involved are properly scaled, right? So similitude is a condition which will exist only when the physical parameters are properly scaled and not just the geometry. Okay, so this figure we have seen before. For this model that you see within the wind tunnel, for it to be an actual representation of the prototype, it should be scaled in a way that many physical parameters are properly scaled and not just the geometry. Okay, all right. Now, the key idea is in similitude, we have three main parts. Okay, number one is geometric similarity. Okay, and number two is uh, kinematic similarity, and third one is dynamic similarity. Now, what do we mean by all these three? Now, when I talk about geometric similarity, it means that ratio of geometric proportions is common, right? Say, for example, the length of the model divided by length of the prototype, or breadth of the model divided by breadth of the prototype, or similarly you can talk about the height of the model by height of the prototype. This ratio should be constant, right? Now this will hold good to with respect to volume and surface area also, which will be length squared and length to the power 3 for volume, right? Therefore, those ratios of length, area, volume has to be constant. This is what we mean by geometric similarity, right? Now, what do we mean by kinematic? Now, here what happens is the uh, the flow patterns must be similar. Okay, the like streamlines that exist in the prototype and in the model must be same. For here we talk about velocity at a point in the prototype, okay, must be proportional to the velocity at the same point in the model, right? Typically, we talk about direction of flow. Velocity being a vector, the direction of the streamline, the direction of flow at a point in both prototype and model must be same. All right. Then we come to the last one, most important, dynamic similarity. This is where we take into account forces, right? The forces that act on the prototype, right, should be, that ratio should be same in the model also. All right. Now, in simple terms, I can say that geometric similarity will make sure that the prototype and the model looks the same. All right, and the kinematic similarity, it will make sure that both the prototype and the model will have similar movement. Okay, the motion of both structures subjected to airflow is same, whereas dynamic similarity is the one which will make sure that the prototype, the effect of forces on the prototype and the model feels the same. Okay, so looks same, moves same, and it will feel same, right? Therefore, this is what we mean by similitude. Okay, now I just want to ask you one question. Which do you think is more important? Is it same shape, same motion, or same forces? Please, put your answer in the chat board. What do you think is more important? Are all the three equally important? Saurav says that same forces is like important, and Hussein says shape. Okay, and Amit says all the three. Okay, uh, Ashwini also says all the three. Now, that is true. Okay, all three similarities are like important, but just for the end effect purpose, I will say that the dynamic similarity stands slightly, more important. Okay, because unless the forces match geometrically, both prototype and the model may look very similar. If you will scale it down, they just look the same. But it's if you will do a study, you will get wrong answers if the forces doesn't match. Okay, so I will say that dynamic similarity is more important. Okay, okay. So now, if you will look at geometric similarity, what you see here is you have a prototype of a ship and you have a model. Okay, now proportionately, the length angles should be in the same ratio. Okay, the scale factor should be same. Okay, for both length of the prototype by length of the model, breadth and the height, the proportionately it should be the scale factor should be same. Right now, when we talk about kinematic similarity, what I'm saying is, if you look at this spillway here, okay, now this is a spillway from a assume that this is a spillway from a dam, right? Now on the left is the prototype. If you see at point A, velocity of the prototype at point A, it's acting in a particular direction, right? That same point in the model, direction of the velocity must be same, right? The same way, acceleration at point A, right, and acceleration of the same point in the model, both should be similar. Same holds good for B as well, right? Now, why is this like important? It is like important because we actually know that when fluid flows, all right, and if there is a sudden obstruction, okay, there will be formation of vortices. There might be formation of fluid separation and so on. Now, if that happens in the prototype, it should be exactly captured in the model as well, right? If like that doesn't happen, then your analysis will be actually wrong. All right. So now, if you see below, what happens when there is kinematic similarity is, if I take the ratio of velocity of model at point A to velocity of prototype at model A, that ratio will be same, and that's also good for acceleration also. Okay. Now, when acceleration scale is same, right? You can also take that the time scale also becomes like important. Okay, how much seconds does it take for a fluid particle from to move from point A to B? Okay, in the prototype that is TP. Okay, and what is the time that is taken for the fluid particle to move from A to B in the model? That ratio is also like important, right? Now, time we know is length by velocity, isn't it? Because velocity we know is distance traveled by time t. Okay, therefore t will be length by velocity. Therefore, that ratio for both prototype and model has to be same. Okay, therefore, for the time scale to match, the ratio of length to velocity in the prototype and in the model has to be same. Okay. Now, moving on. Uh, yeah, okay. Now this, yeah, okay. Now, moving on, the third aspect is, when do we say that dynamic similarity exists? Now, this is when the forces that acts on the prototype and model are proportional or same. Say, for example, when you have a cargo ship, okay, and some of the important forces there is definitely gravity is like important, right? Then we have the viscous forces acting through the fluids because it is moving on the fluid, isn't it? Therefore there will be fluid friction. Okay, therefore viscosity is very important. Then there is pressure acting on the structure of the ship. Okay, and since it is a massive ship, it will also have significant inertia, right? Therefore, there are four forces here. Okay. Now, when you build a model, the effect of these forces on the structure should be similar. Okay. Therefore, if suppose if I feel that gravity is more important And if I take the ratio of uh, inertia force to the gravity force in the model, it should be same as that of the inertia force and gravity force in the prototype. Okay, therefore, the model should reproduce the exact force balance in the prototype. Okay, that ratio of forces in the prototype should match that of the model. All right. Now, what are the various forces that act in fluid flow? Okay. Now, we have studied many fluid forces. Now, I have made a list of some of the important forces that exist in fluid flow. One, as usual, it is inertia force. Then we have pressure forces, especially when you're dealing with flow through pipes, when fluid is flowing through a closed pipe, then we say that pressure becomes like important, right? Similarly, lubrication flow systems might showcase dominance of viscosity, right? Open channels, storage tanks, gravity becomes very important. Now, if you are talking about nozzles, if you are talking about fuel spray, then surface tension force becomes very important. Okay, then there is elastic or compressibility force. Okay, when we actually talk about fighter jets moving at Mach 1, Mach 2, okay, here the compressibility effects becomes very important. Okay, then buoyancy, right? Buoyancy is also a significant force that acts on structures which are, partially submerged in fluids. Similarly, in some unique applications, electromagnetic forces also plays a role, normally in nuclear reactors and so on. Okay, therefore, these are all the forces that act. Okay, now what I want to ask you is, in pipe flow, which force do you think is most important? Can someone answer? Can you make a guess? Viscous force is very important, is what advice says. Advice says that viscous force is very important. Absolutely. Okay. Viscous forces are very important when in a pipe flow. And along with that, inertia forces is also like important because you have a body of fluid which has to move, right? Therefore, effect of viscosity and inertia becomes very important. Okay. Now that leads me to another example of. Let us look at a pipe flow case here. On the left, you see a prototype. Okay. Now fluid is flowing through this pipe. Now I need to create a model which is an actual representation. Now, what are the variables of like importance here? Okay. Obviously, since we have to make diameter is an important variable, isn't it? Right. So for D is like important. Velocity of the flow is also like important, right? Similarly, since the fluid properties are important, density and viscosity also becomes like important. Okay. Now, what is happening here is I've got four variables here, right? Now, I to prepare the model, I will have to scale each one of those variables. I have to design the model such that all these variables are actually scaled. Okay. Now that is difficult, isn't it? It becomes impractical to like scale all these variables, and some of these variables you will not be able to scale at all, right? And it is like not easy, right? Now this is a problem. This is a practical problem. While we want the model to behave like the real system, which is the prototype, we it is not possible for us to match every variable directly. Okay, how do we solve this problem? This is where we make use of dimensionless numbers. Now, in the previous module, Nishigan sir has taught you about dimensionless numbers. You have learned Buckingham's pi theorem. Yes, okay, you have learned how to create dimensionless numbers by looking at the repeating dominant variables through a structured process. You are able to derive dimensionless numbers. Okay. Now, our problem of scaling becomes easier when we make use of dimensionless numbers. Now, what are this? Now, in dimensionless numbers, what we do is instead of scaling each and every variable, we will group them into dimensionless groups. Now, suppose if you look at the same problem of pipe flow, in the prototype, we had four variable: diameter, velocity, density, and viscosity. Right now, to prepare the scale down model, what I have to do is I have to group these variables d, v, rho, and mu such that they form a dimensionless number, meaning it will not have a unit. Right? This doesn't have a unit. It is independent of dimensions, meaning this number, if it is, will apply equally to a big size structure and a small size structure. Size doesn't matter to this number, right? Therefore, this is a dimensionless number, right? So we can group diameter, velocity, rho, and mu as rho vd by mu, which will end up in a dimensionless number known as Reynolds number. This is a very important dimensionless number which we use in fluid mechanics, right? Now, for the prototype and the model to showcase similar behavior, all you have to make sure is that the Reynolds number of the prototype flow should match the Reynolds number of the model flow. Just by matching one number, we get similitude. All right, that is REM, Reynolds number of model, is equal to Reynolds number of the prototype. That is rho m, vm, dm by mu m matches that of the prototype. Okay, this will ensure that similitude is maintained. Okay, now let us apply this. Let us apply this to a simple problem and see how it works. Okay, now let us assume that there is a real cooling pipe, okay, through which a coolant is flowing. Okay, water is flowing through that. Okay, and this cooling pipe has a diameter of 1 meter. Right, water is flowing through it at a velocity of 2 meters per second. Actually, okay, in the prototype. Now, I have made a laboratory model by making use of 1:10 scale. That is, I have made it smaller by 1/10. Therefore, the diameter, which was 1 meter, is now 1/10, 0.1 meter. Okay. Now we assume that the fluid is same. Fluid is same in both model and the prototype. Okay. What is my task? I have to find out what should be the velocity in the model such that the flow behavior is same. Right? For the flow behavior to be same in both prototype and model, what should be the velocity of the model? This is the problem. Now, therefore, you can see here prototype is 1 meter, model is 0.1 meter, velocity in the prototype is 2 meters per second. What should be the velocity in the model, which is scaled down by 1:10? Now, you can obtain this velocity in the model directly by making use of the Reynolds number. Now, before that, I want to ask you something. The pipe has become smaller by 1/10. Now, what do you think will happen to the velocity? Will it become more? Will it remain the same or will it decrease? Please answer. Uh, Ashwini says velocity will increase. Okay. Advai also says it will increase. And uh, Tanuja says more. And Hussein says, sorry, increase. Okay. And Advai says that it will increase by 10 times more. Absolutely. You're all proper there. The velocity will have to increase. Let us see why and let us see how. Okay. Now, let us go ahead and solve this problem. For pipe flow, similarity, the Reynolds number must match, isn't it? So for the Reynolds number in the model should be become same as that of Reynolds number in the prototype. Therefore, rho Vd by mu for both model and prototype has to be same. Now, since the fluid is same, since water itself is flowing in both prototype and the model, the density and the viscosity variables can be taken out. Okay, therefore rho and mu from both sides will go off. Therefore, you have Vm equal to Vp dP, and from this you can find out velocity of the model. So let me substitute the answers 2 into 1 into point 0.1, and I get the velocity in the model as 20 meters per second. In the prototype, it was 2 meters per second. Now it has become 20 meters per second. Therefore, even though the model becomes 10 times smaller, the velocity must be increased by 10 times to maintain similar effect on the model, right? For the model and the prototype to experience similar effects, for the Reynolds number to become same, velocity will become 10 times greater. Okay, so you have seen how dimensionless number helps us in getting good models, okay, valid models. Now, what are the commonly used dimensionless numbers? These, I have made a list of 5 dimensionless numbers here. One is a Reynolds number, right, where which is the ratio of inertia force to viscous force. Okay, this is usually applied in flow through pipes, okay, or even in airflow over vehicles where viscous or viscosity dominates. Okay, when gravity dominates, when gravity forces becomes very important, such as open channel flow, ship motion, and all that, we make use of root number. Root number is velocity divided by root of gravity into L. Similarly, when pressure forces becomes very important, say when we talk about pumps, okay, pressure is very important, isn't it? And especially when there is pressure drop within a pipe, okay, loss of pressure, right? We talk in terms of Euler number, all right? Then there is Weber number, which takes into account surface tension force. Okay, typically when we deal with formation of drops and fuel sprays, this where surface tension becomes very important, right? We make use of a Weber number. Then we have Mach number, which many of you would have heard about it. It relates velocity to speed of sound. Why? Because at very high speeds, right? Very high speeds, density of the fluids will change, right? And this change in density will lead to compressibility effects, which is actually change in density, right? Now this happens at high speed gas flows. Okay, here we make use of Mach number, which is velocity of the projectile divided by speed of sound. Okay, now I just want to ask you something. Which number is important for pipe flow? Which we have already seen, isn't it? Therefore, there is no point in asking again. We actually know that for pipe flow, Reynolds number becomes like important. Now, based on these dimensionless numbers, based on this dimensionless a number, uh, there are a few set of laws which will help you uh, help you obtain similitude and help you in your model design. All right, that is, uh, you know, the main idea is if you focus on dynamic similarity, right? That is, when you will take the ratio of forces in the model and prototype and make it same, right? Then your model issues becomes very less, because as I said, dynamic similarity is very important. Okay, and since dimensionless numbers matches are obtained by taking into account the forces that act, right? But then the problem is we cannot match every dimensionless number, isn't it? Therefore, it is important for you to identify which is the dominant force, right? And get the appropriate dimensionless number and match it. Okay. And that is what we mean by model loss. Model laws will look at the dominant forces and then help us create appropriately matching prototypes and models. Okay. Now, five commonly used model laws are shown here: Reynolds law, Froude law, Euler law, Weber law, and Mach law. Okay. Now, let us quickly look at what we mean by these laws. Reynolds number, you have already seen it now. We will solve a problem based on that. Okay. Now, this is an interesting problem. Please pay attention here. Now, we are a prototype pipe which is of diameter 1.5 meter. It carries oil. Okay. Oil is flowing through this pipe. Specific gravity is zero point 0.9. Viscosity is 3 into 10 raised to power minus 2 poise. And there is a discharge of 3000 liters per second flow. Okay. Now, we are creating a model of it, which is 15 centimeters only, okay, which is 0.15 meter, right? Now, and to test this model, I'm not using oil, but I'm using water at 20 degrees Celsius, right? Now, this important learning here is to test the model. Sometimes we may have to change the fluid so that we are able to represent the actual prototype experience, right? Sometimes we may have to change the water for practical purpose. Okay, this becomes clear when we solve a future problem. Okay, now find and they're asking you to find what is the model velocity and what is the model discharge. Okay, therefore we need to find out Vm and uh, Qm. Right now, what we do is we will match the Reynolds number because this is a pipe flow. All right. Now, when you match Reynolds number of the model with that of the prototype now, we cannot ignore density and viscosity. Why? Because in the model it is water, and in the prototype it is like oil. Therefore, you cannot take it out. Okay, so you keep all the three ratios of density, diameter, and viscosity, and you get the velocity ratio, Vm by Vp. And we get the relation that velocity in the model should be three times that of velocity in the prototype. Okay, now you can substitute, okay, because they have given you the discharge for the prototype. How much is that? 3000 liters per second or 3 meter cube per second, right? Therefore, substituting that, you will get the velocity of the prototype as 1.697. Okay, right? And because we know that discharge is area into velocity, right? Q equal to AV. You have already studied this. Therefore, velocity in the prototype becomes 1.697. Substitute it here, and we get the velocity in the model to be three times that. Therefore, velocity in the model should be greater. It is 5.091 meters per second. So this is how we obtain velocity in the model. They have also asked you to find out what will be the discharge in the model. So you find out Qm, area into velocity, substitute it, and you get the answer as 89.9 liters per second, right? So this is how you can apply Reynolds model law when viscosity is the dominant force, and you can design the model. Okay. Similarly, Froude model law. Froude model law, I said, is important when gravity is the dominant forces in spillways, nozzles, surface waves, okay, and at the surface of two different fluids. When you're designing things like this, Froude model law becomes like important. And Froude number we know. I'm sorry, I just lost the screen. Just a second. Uh, is my slide visible?
Yes, sir.
Okay. So this is the Froude law. Uh, okay. So in like Froude law, the two dominant forces here are your inertia force and the gravity force. Now, these two should balance. Okay. Now, let me directly go to a problem there. Uh, we are losing time. So, see, now in this problem, we see that a spillway model, it's an open flow. Therefore, uh, your law becomes like, just a second. Yeah. Okay. Now, here the problem states that a spillway model is built at a scale of 1 is to 40. Okay. And in the model, a velocity is 2 meters per second, discharge is 2.5 meter cube per second, right? Find out the appropriate prototype velocity and prototype discharge. All right. So you've got now, since this is an open channel flow where gravity and inertia becomes like important, we look at Froude law. Okay, then we will find out. See, the length scale we know it is already given as 1 is to 40. All right. Now, similarly, we'll have to find out, we have to substitute and obtain velocity of the prototype. All right. I mean, the model it is 2. If it becomes 2 into root of 40, therefore, velocity in the prototype is 12.65 meters per second, right? Now you can do the same thing and find out a discharge as well. Okay. Okay. I'm going to speed up a bit because it's almost 1 hour now. So, all right. So the final answer is velocity in the prototype is 12.65 and discharge is 25298.22 meter cube per second. Now, the next important number is Euler model law. Now, Euler model law is typically used when pressure effects are more dominant. Okay, therefore, when we have flow through a nozzle or when we have flow through a hydraulic machines where pressure drop becomes very important. In such cases, we make use of this particular Euler law, which is Euler number, which is P by rho V square. Okay. Uh, Now here we can get the pressure drop. I have derived this law here. I will share the slides with you and you can go through this. Okay. Therefore, equal Euler number in both model and prototype is like important. Okay. Then we have a Weber number. Weber number, as I said, is important when you are dealing with fluid droplets. Okay, when you form bubbles and when you are dealing with air bubbles in capillary tubes. Okay, when we want to know how long will a jet uh, remain without breaking up. Okay, or what will be the diameter of a fluid drop. Okay? When we are dealing with those sort of problems, it is important to make use of Weber model law. This is the ratio of rho v square L by sigma, where sigma is surface tension. Okay, surface tension forces and inertia forces are more dominant here. Okay, all right. So this is also same. Let me go forward. Then we have Mach number. Mach number, as you would have already learned, is similarity when fluid the compression becomes more dominant. That is, the speed is such that density will change. Right now, when that happens, especially with fighter aircrafts and so, at high speed flow, you will you will have to make use of Mach numbers to design the model. Okay, the Mach law will be taken into application here. Okay, and Mach number we know is m is equal to v by c, where c is a velocity or speed of sound, which is given by root of by rt. Uh, okay, this is explanation for the Mach number and how to derive it. You can go through this on your own. Now, this is a problem that I wanted to solve. Let us very quickly go through this. Okay. Now, in this, what is happening is the pressure drop, which provides the lift in an aeroplane. Okay, we are preparing a model of it of size 1 by 10. We are scaling it down by 1 by 10, right? And the pressure drop is 80 Newton per centimeter square. Okay. Now they say that the model is tested in water, right? Now this is sort of strange, isn't it? Why should you test a aircraft in water, right? It is like important. We will see why it is like important. Okay. Now find what they are asking is find the corresponding pressure drop in the prototype. Okay. Air density is 1.24, viscosity is zero point zero 0.01 poise, and the air viscosity is 0.00018 poise, right? So we have to find out what is the pressure drop in the prototype. Okay. All right. So here we make use of two models simultaneously, right? Now, this is why I wanted to show this. Okay. In applications, depending upon the dominant forces, you may have to choose one or more laws to prepare the model. Now, here Reynolds law is like important. Why? Because viscosity is like important here, right? At the same time, pressure drop is also like important because it is the pressure drop that gives you the lift. Okay. Therefore, in designing this, you have to take both Reynolds law and Euler's law, both should be taken into account. Okay. Now, one thing is, why are we testing a flying object in water and instead of air? This is because to obtain the high speed effect in air, if you create a model, okay, we have seen how velocity becomes very high, isn't it? Velocity in the previous problem was the model velocity was 10 times that of the prototype. Okay, here the aircraft speed is very high, velocity is very high. Now, to get that same effect in a model, velocity will become too much. It will not be humanly possible for us to test that a model. Therefore, what we do is we immerse it in water. And water, since it has higher density, what will happen is that same effect of the prototype, you can inflict that same effect in the model at a reduced velocity, at a more practical velocity. Okay, so this is why it's been done. Now, in the same way, we will begin with Reynolds number. We will match a Reynolds number of both model and the prototype, and we get the velocity of the model. Okay, as 0.6889 times velocity of the prototype. Okay, then we will go into Euler's model, where we will match the Euler's numbers, and then we will obtain the pressure drop at the prototype as 0.209 Newton per centimeter square. Right. So you can see that the a pressure drop is 0.209 Newton per centimeter square in the prototype. Right. So you can see that the pressure drop in the prototype is smaller than that of the model. Okay. All right. So this was an interesting problem. I just need 5-10 minutes more. Now, so you have now understood how uh, similitude works, how geometric, kinematic, and dynamic similarities are like important and where they are applied. We have also looked at dimensionless numbers and how it works. Okay. Now, why do we need? What are the objectives of model testing? Okay. As we spoke, it is you know it is very important that we predict behavior of real systems using scale models because it is not possible for us to build the real system and then test if it is fail safe or not. It becomes very expensive and very risky. Therefore, model testing is like important. Okay, and there are cases where the fluid flow is very sophisticated, where theory becomes difficult for you to apply these theoretical equations, it becomes difficult, and the only choice then is to experimentally check. Okay, now and model testing is also done to ensure that your performance is as expected, right? And sometimes if you need design improvements, we will get that design improvements early on in the design process. Okay, now model testing is very important. Now I also want to talk to you about these days our computational power has become very strong, isn't it? We have got wonderful analysis tools. We have got CFD, we have got ANSYS, we have got OpenForm. Okay, there are so many simulation tools, but still, why do we have to do model testing? It is because your simulation results also needs validation, right? Therefore, model testing is invaluable. It has to be done. Okay, normally what we do is we will mount sensors on the models, get the data, use it in our simulations, and then check the prototype performance. Always keep in mind, simulation is not an excuse for not doing model testing. No. Okay, you have to do both simulation and model testing simultaneously. All right. Now, applications, there are plenty of applications. In those problems itself, you have seen pipe flow systems, pumps, and turbines, right? And uh, nowadays, there is a lot of applications of fluid flow in electronics as well. All right. Okay. So with that, I'm done with my presentation. Now, before I end, I just want to, ask a few, like small quiz here, right? Can you please answer this question so that we can reinforce the learning that you have had? Okay. In similitude studies, what do we call the actual engineering system and the scale down version? Please answer this. What is the answer for this? Model and prototype. Agree. All right. Now let's move on to the. So the answer is actual engineering system is prototype and the scaled down version is model. Now, can you name the three types of similarity required to ensure similitude? We actually spoke about this, isn't it? Similitude has three aspects to it. What are those three? Number one is geometrical, then uh, kinematic, and dynamic. Prasanna is proper. Prasanna has properly entered all the three. Advai has also mentioned length, Reynolds number. Saurav forces, shape, motion. Yeah, I mean, in a way, that's also proper. Okay, so it is shape, motion, and force. Actually, the three terms are geometric, kinematic, dynamic. Same shape, same motion, same force. Next one. For pipe flow or cooling line problems, which dimensionless number must be matched between model and a prototype? Which is the model? Which dimensionless number is like important? Aditi says Reynolds. Prasanna and everyone says Reynolds. Answer is proper. For pipe flow, most important dimensions number is Reynolds number. Next, for which model law is most important for spillways? Dam spillways, open channel flow, and ship wave problems. Okay, which is the important model law there? Is it Reynolds Froude? Okay, Saurav says Froude. Absolutely, that's correct. Okay, so Froude model law is important for open channel flow, where gravity effects is dominant. Okay. Next, last question. A prototype pipe carries water at a velocity of 2 meters per second. We are making a 1:10 model using the same fluid. Okay. Now, what model velocity is needed for similar flow. It is 10 times, absolutely. So 10 times 2 is 20 meters per second, right? So the answer is 20 meters per second. All right. So with that, I'm done with my presentation. Thank you for your patient listening. I am open for Q&A now. So if you have any questions to ask, please go ahead. Thank you, Prasanna. Thank you, Saurav. Any questions? I'll be more than happy to answer.
Is there any
Abir,
questions?
Abir is saying, I think pressure forces are also important for pipes. Absolutely. Because for fluids to flow from point A to B, there should be a pressure difference, isn't it? Otherwise, flow doesn't happen, right? We like talk in terms of pressure drop, right? But Euler number directly deals with that. Okay, but for regular, if you are talking in terms of forces, if you're talking in terms of forces, then viscosity and inertia becomes like important. Okay, all right. Sir, does the material of the model we are gonna test affect anything? Absolutely. Okay. Now, what happens is with material, we typically maintain direct link between the prototype and the model. Okay, both are usually made of the same material because usually in model testing, what are we looking at? We are looking at structural integrity, right? We like want the structure to bear the temperature and the stress effects, right? Therefore, material of the model is usually kept same as that of the prototype. Okay? Yeah. Abir says pressure losses play a major role. Absolutely, it is. It does. So material, what would you suggest? As I said, typically what material we apply for the prototype, we will have to use the same material, right? As far as possible. Okay. Is it possible to consider two dimensions? I think you mean Amit. You say it is two dimensionless numbers. No, absolutely. There are many applications where multiple dimensionless numbers will have to be taken into the account. And please don't go with only those dimensionless numbers which I've shown in the slides. No, okay, you will have to derive dimensionless numbers using Buckingham's pi theorem for the application that you are working on, right? To actually create the right model, you will have to identify the repeating variables and define suitable dimensionless numbers of your own as well. Okay. Saurabh says why we use water instead of sorry, that is getting blocked. Okay, instead of air in testing aircraft. As I said, Saurabh, when we are designing aircrafts, it has to withstand very high velocity, isn't it? Suppose if we are testing a fighter aircraft working, operating in Mach 2, the velocity is very high. Now, I will not be able to simulate that same velocity in the model, right? Because it will be practically difficult to make the model move at that particular speed or to move air at that particular speed over the model. Therefore, what I do is when I use water, I don't have to I don't have to move the fluid at that high speed because the density is more. By operating the fluid at much lower velocity, I am getting that same effect on the model. Okay, say for example, if the structure of the prototype when it is moving at Mach 2 goes up to say 250 degrees Celsius, then that same effect you can simulate it in the model by making use of an higher viscosity fluid or a higher density fluid, okay, at lower speeds. Okay. Some other questions. How can we integrate IoT or AI ML techniques for this as in future advancements? Advai, it's not future, it is already happening, right? Because if you look at a wind tunnel experiment, there is significant Internet of Things there. Okay, and AI is already there in almost every computational study that we do. Okay, so that integration is already happening right now. It has already happened also. Okay, what are the factors on which the margin of error between the model and prototype analysis depend, as 100% accuracy is not possible. 100% accuracy is not possible, and in most cases, it is not even needed, but it should be as close as possible to the actual prototype performance. Okay, see, if the physics is strong, say for example, if we are dealing with the fighter aircrafts and your normal aircrafts, that physics is well understood, isn't it? We have close to 100 years of experience with it, so we know how it works. So the physics is sound, physics is strong. Therefore, the prototype testing need not be 100%, but as close as possible. But suppose if we are designing a spacecraft, right? Now that is something new, right? Suppose if we are designing a spacecraft for Mars, right? Now that environment is new, okay? So for there, your model and prototype accuracy will matter a lot, okay? All right. Any suggestions for future advancements? There are plenty of research happening, Advai. Okay. If you will, log in and search for latest research in prototyping and modeling, there are plenty of work that is happening. Okay. Say, for example, in the field of shipbuilding. Okay. In the field of shipbuilding, there is something known as towboat studies, right? Where you will move the structure at the speed of an actual ship. Okay, now there is a lot of research that is happening in it. Okay, so you can please explore it. Anything else that I can answer? I think I've answered all the questions. If I have missed something, you can please. Sir, can you share the resources for learning of similitude and model analysis? Absolutely. I mean, I can share this PPT with you. I will share it with Dr. Neshigand, and you can take it from him. I think I've answered all the questions. Yeah.
Okay. Thank
All
you
right.
so
Yeah.
much,
Thank you.
sir.
Yeah.
Yeah. For your
I'm sorry, Ashwini. There is like one more question. If model and prototype have varying heights, then which height should be chosen for a ratio? No, you can't have. See, the height ratio of model and prototype has to be same. Okay, the scaling factor, that ratio has to be same for both model and the prototype. Okay, Amit. All right. Okay. Go ahead, Ashwini. Yeah. Thank
Okay,
you.
thank you, sir. So, thank you so much for your valuable words. Your guidance has truly added great value to this session. We hope today's webinar on similitude and model analysis in fluid mechanics has enhanced everyone's understanding and provided practical insights into the real world applications of fluid mechanics. So, for participants, dear participants, the feedback form for today's webinar will be shared in the WhatsApp group shortly. I request everyone to kindly fill it out and share your valuable feedback with us. Now, I would like to hand over the session to Nishigand Gorde, sir. Sir, over to you.
Thank you very much, Ashwini. Uh, there is Dr. A.V. Wagmare, sir, from Ishre Pune chapter student chair with us. Sir, please say something. Wagmare, sir, is there?
Yes, sir.
1 minute, sir. Please, sir.
Yes, sir. Yes, sir. Thanks for unmuting me. Just a minute. Uh, Actually, the question answers were very resourceful. The students were asking questions, and then the sir was answering to them. That was very or that added the value in our webinar. And this webinar was really important in such a way that the students are having this as a subject, and then you have chosen this topic as an important topic from the fluid mechanics. We also taught this subject, but the our teaching was the exam oriented, and this is the knowledge oriented. And really hats off to you, sir. The very well explained this topic.
Thank you so
And
much.
I would suggest one thing that if possible, the recording can be shared, and then this presentation also, and then the students will again respond to a user. I'm sure that the respondents or the participants will be in touch with you for more in detail. So thanks for allowing me to say a few words on this. Thank you,
Thank you,
and
sir.
handing over to you.
Thank you, Wagmare, sir. Sir, I will definitely share all the PPTs and all the materials after receiving from Binu, sir. Sir, thank you very much for your wonderful and interactive session. You explain about the what is fluid statics, dynamics, model, prototype simulated, then geometric, kinematic, dynamic similarity, along with dimensionless numbers, models, and similarity laws. I am very thankful to all the participants on the behalf of Jain College of Engineering, Mechanical Engineering Department, and ISHRE Pune chapters for attending the national level webinar. I confident that you all get lots of knowledge today. I also thankful to Pawar sir for permitting and assigning me as a coordinator for this webinar. I also thankful to our Dr. Ubale, Principal Sir of Jain College of Engineering, Dr. D.S. Galle sir, Chief Executive Officers, and Dr. Shubhangi Gunjal for unconditional support for ISHRE activities. And also thankful Ashwini for your volunteering today.
Thank you so much, sir. Thank you for the opportunity. I hope it was useful, and looking forward to more interaction